Hello, everyone. Welcome to the VaNTAGe seminar. So we're continuing our series of talks on profinite groups and Galois groups. And today we're very happy to have Ravi Ramakrishna, who's going to be talking about Ozaki's theorem. I see some people are still coming in, so let me just repeat that today we're having Ravi Ramakrishna talking about Ozaki's theorem. And Ravi, is it all right if we record this talk?
Yes, it is.
Wonderful. And if you have questions, please feel free to ask them during the talk. Okay, Ravi, go ahead.
Yeah, I can't tell because my picture is small. Yeah, thank you. I want to make sure my whole board is in the picture. Okay. Thank you for the invitation. Most of what I talk about today will be joint work with Christian Mer and Farshid Hajir. And I want to start off with two hopefully easy things. Just as a warm-up. The first is that 2 divides the class number of the field you get by adjoining the square root of 29 times 5, and it divides the class number of the field you would get by adjoining the square root of 13 times 5. And I'll very quickly do one of these. Maybe I'll do 13. We have this field diagram, and of course this field is in the middle. I'll give this a name because I don't have much room in there. Now it's pretty easy to see this is ramified at 5. This is ramified at 13. The ramification index is 2 here, 2 there. This is unramified at 5, and this is unramified at 13. So this field absorbs the ramification at both primes, which forces this to be unramified. And because it's unramified, that means the class n degree 2 has to divide the class group. And the same thing works with 29. But in fact, okay, yeah, all right. This class number is 4. And this class number is 2. So why the difference? And let me prove that this class number is 2. Well, I'm not going to prove it's 2. I'm only going to be studying the 2 part of it, so I'm going to prove that 2 divides it. That's the highest power that divides it. And the idea is you suppose not. And I'm going to skip some steps here. But if not, that means that there is another Z mod 2 extension, or 4 divides it at least. And what you'll have is some unramified extension J over K that will be unramified, that will be quadratic. J degree 2 and unramified. Okay. But what that tells us is, and you have to play, it's an exercise. You have to play a game, and you can make sure that J is Galois over Q. If there's too many of them, you can sort of, it's not hard. That really would be a homework problem. So then what is this? This is either Z mod 4 or Z mod 2 squared. And we'll just eliminate both cases. Well, one thing is, this class number is exactly 2. Is 1. But I'm not worried about the odd part. I'm just going to prove that 2 does. I'm just going to state 2 does not divide this. and I'm not going to prove this. This goes back to genus theory of Gauss. Okay, so there's the two cases. And the point being that if you're Z mod 4, we're ramified at 13, but we know that this is unramified everywhere. We're assuming that. So the ramification index of 13 is 2. So it has to land in the only subgroup of order 2 in here. And therefore, that would fix an unramified extension of degree 2 over q root 5. Or we get a contradiction. Okay, and if it's Z mod 2 squared, and this is where the really important thing comes in, we're going to get a contradiction, so I'll write it up, but let me explain why. There's only one prime above 13 in q root 5. You got to do some quadratic reciprocity, but that's pretty easy to see. Because there's only one prime above 13 here, and the class group is prime to 2, if you allow ramification at 13, you're only going to get one extension. You can't get two extensions. Only one Z mod 2 extension ramified at 13. And if you want to ask what's the difference between 13 and 29, 29 splits in this field. So there are two primes above 29, and that's what allows this class number, when you switch to 29, to be 4. Okay, so that was the first, hopefully not too bad thing. Let's switch gears and go to the second not too bad thing. So I have 4 questions on the board. Is there a quadratic extension ramified at exactly the prime 3? And we know the answer to this. 3 is not 1 mod 4, so the answer is no. 7 is not 1 mod 4, so the answer is no. 21 is 1 mod 4. The answer is yes. Now, 3 times 5 is not 1 mod 4, so the answer is no. But if we allow infinity, then secretly what I'm really saying is negative 15. And the answer is yes.
So do you mean real quadratic?
No, just, well, so my point being that ramified.
Oh, infinity. Okay.
Yeah, means I'm allowing complex quadratic. If I'm not allowing infinity, then I mean real quadratic for these 3. Okay? Great. And it's nice to see you, Ralph. Okay. So we have the answer to these questions, but I actually don't think that this is the right way to think about it. So what I want to do is look at Q and Q adjoin I. Frobenius at 3 in this extension is non-trivial. 3 does not split, nor does 7. 5 does split, so its Frobenius is trivial. And infinity, I will say, has non-trivial Frobenius as well, because the infinite place ramifies here. So I know there's a little bit of a weirdness with calling it Frobenius and using the word ramified, but we'll live with the weirdness at things with infinity in 2 like we always do. So Frobenius at 3, that Galois group, is not the identity in G. Frobenius at 7 is not the identity in G. Frobenius at 5 is the identity in G. And Frobenius at infinity is not the identity in G. And what I really think is the right way to think about this is do the sum of the Frobenius elements add up to 0? And if the answer is they do add up to 0, then we put a yes. This is the non-trivial element in this Galois group. We add it to the non-trivial element. That's 0. Non-trivial, trivial, non-trivial. They add up to 0. These two are both non-trivial. This is, to my mind, the correct formulation, which is not, at least when I was learning algebraic number theory, was not taught this way. I mean, this is a standard thing that I'm sure everyone has seen. But now I'm going to come to something that maybe not everyone has seen. A theorem of Grandmonnier from 1997, which I mean, I don't know the history of this, but I imagine people knew about it and then they forgot about it and it was rediscovered. But it's such a beautiful result that it's sort of surprising to me that it was not a standard in textbooks when I was learning mathematics. So we're going to let K be a number field. I'm going to just let P.
Excuse me, I have a question.
Yeah.
So your 0 in Galois group G. So can I understand that it is the E you mean?
It will be what?
E, I mean, is it 0 or E?
Oh,
Because
E is the identity. Yes, I'm sorry. Yeah, it's
yeah, but
oh,
yeah, above you wrote.
yeah.
Okay.
Thank you. Thank you for pointing that out.
Yes.
Yeah. Switching from multiplicative to additive group structures. That might happen again. And we'll have P be an odd prime. And we'll let Q1 to Qn be primes. It doesn't have to be odd, but it's just easier, and I don't want to waste time on the edge cases. Odd primes of norm congruent to 1 mod P. So you can ask the same question. Is there a Z mod P extension of K ramified at exactly this set of primes? That's the general thing of that quadratic thing that we all learn in the beginning of an algebraic number theory class. I'm going to write this down and I'll have to explain it in a moment. So I have a linear combination of these Frobenius elements adding to 0. I haven't said where they live. I'm going to say that in a second. But,
Makes sense.
but the point I want to make is when P was 2 in this previous case, the only non-zero coefficient is 1. So that's why it had to be a sum. But now we have a little bit of room to move around. And what's going to happen is we're going to add in the pth roots of unity. And then we're going to add in the pth roots of something called the empty set, which you may or may not have seen. And my Frobenius elements are going to be living in this group. Okay? And let me just briefly say something about the empty set without going into too much detail. What I'm about to write down should not be a surprise. Namely, the empty set is some complicated thing. What's complicated about number theory? It's untangling the units in the class group, right? So what's happening is we have an exact sequence like follow. I'm not going to define the empty set. But I'm just going to say it sits in this exact sequence. Where you have the units of K mod p powers, the p torsion of the class group, and somehow this thing is those two units in class group put together. And basically, we just need to check how primes split in here. And that, by the way, is something Chebatarov's theorem will tell us. When we know how primes split in here, we can get such dependence relations. And this is the Gromonier theorem. So that thing we learn about quadratic fields ramified such and such primes away from 2 anyways, in the first week or two of an algebraic number theory class, there has been a generalization for that. And like I said, this theorem is 97. As far as I know, no one ever wrote it down prior to that. Okay. And I'll just say, maybe I'll make a remark that in, when was this? 2023. With Hajir and Meir, we proved that the cardinality of the set of such dependence relations where all the coefficients are non-zero equals the cardinality of those F in, I'll write it down here. And I'm not done yet. So this is the Galois group of K ramified at these primes only with trivial action on Z mod P. So these are just Hams. Now, some of the Hams could be unramified and give rise to unramified extensions, but I'll insist that they be ramified at all primes. Primes. And you have to have these kind of things because any dependence relation you can multiply by a non-zero scalar, the same with a cohomology class. We did not get a canonical isomorphism, but Nicole Johnson, who's a student at Cornell, has gotten that and is working on an equivariant version and lots of other generalizations. Isomorphism and an equivariant version. Okay. So those are the two relatively easy things. Let's see, do I want to? Yeah, let me state a hard thing. And well, as far as I know, this is an open problem. And since the seminar is supposed to be about open problems, let me state one. So let's take a number field K and 2 primes that do not divide its class number. So there are extensions of K where P divides the class number of L1 exactly, and Q divides the class number of L2 exactly. This comes out of genus theory. This is not too hard, especially if you know the Gromonier theorem. So the question is, can you find one field where this where P exactly divides the class number of and Q exactly divides the class number of this field L. To get a field L where P and Q divide the class number is easy. You just take the composite of these two things. But when you switch from here to the composite with L2, you may introduce extra factors. And as far as I know, this is an open question. And I wouldn't say I've thought about it. I mean, I've certainly stared at it for a long time, but I've had no ideas. I haven't even been able to start. So anyway, that's I don't know of any great applications, but it just seems like a fundamental basic question to ask that I don't think we know the answer to. I am undecided personally as to how hard it is. Like, it wouldn't surprise me if it's as hard as the real quadratic fields class number 1 question, that there are infinitely many of them. And it wouldn't surprise me if it were easier, but I'm not sure. Okay.
I have a question.
Yeah.
Do you have information about the degrees of L1 and L2?
Yeah, you can make this degree P and this degree Q. Just like you can create a quadratic extension of Q with class number exactly divisible by 2.
Mm-hmm. I see.
Okay. That really is, if I break it into steps, it's a hard homework problem. This, no clue.
But what if the class number of K is highly divisible by P or Q?
Oh, well, I'm assuming that P and Q
Oh,
don't
okay.
divide.
Oh, yeah. Okay. Sorry.
Yeah, no worries. Okay. All right, we got that. Now, of course, there is the theorem of Golod-Shafarevich from the 60s. Early 60s, I guess, which is that if G is a pro-P group, and H1, the number of generators, is bigger than or equal to H2, the number of relations, G is infinite. Okay, this is purely group theoretical, but it had these amazing number theoretical consequences because at the time, people weren't sure whether if you had a number field, eventually it lay in a principal ideal domain. And if you have an infinite unramified tower, that's not going to happen. And this gave examples. So, well, it's actually, once you have this theorem, it's trivial to give examples of number fields K with what I will call infinite P Hilbert class field tower, which I'm going to abbreviate from now on. Namely, you have a field K and maybe K0 equals K. And then you have K1 up here. And this Galois group is the P part of the class group of K0. The P primary part. And then K2, this Galois group will be the P primary part of the class group of K1, and the tower goes on forever. That's what they were able to prove, that there were examples of such things, because we have a nice bound for H2 when you're looking at unramified towers. In fact, if you have a number field K and you have K infinity up here, and you have this Galois group, which I'll call G empty set of P. The of P means it's a pro-P group. The empty set means it's unramified everywhere. Then H2 of G empty set acting on Z mod P actually embeds. This is not hard, but I'm just going to skip this part, the proof of it. Embeds into this object I constructed earlier. Okay? It's not an isomorphism necessarily, but it embeds into it. Okay. So one obvious thing when you look at this theorem is that the tower is uncontrolled. Remember, we were able to control that tower. We made it be Z mod 2. With 5 and 29, it was Z mod 4. And maybe you could say I can control it to be big, but let's just try to control it to be small. Okay, and let me now state Ozaki's theorem from 2011. Any finite P group you like then Ozaki asserts there exists a number field K of finite degree over Q such that if you go up to the maximal pro P extension, unramified everywhere, it has Galois group exactly G. So any P group you like. In fact, he actually proved more that if you want it to be a countably generated pro P group, he can make that happen. But you have to pass to an infinite algebraic extension. Okay? But we're going to focus on this part. I'll make some remarks. In Ozaki's proof, K is totally complex. And there is no control over the degree of K over Q or the discriminant of K over Q. The field exists, is all he says. Okay, and when I look at this theorem, there are some applications for it, and maybe I'll hint at some things at the end, but it's just, to me, it's just beautiful. And I looked at it and I was sort of stunned that this could be true. And that's why I wanted to spend some time thinking about it. And I did with Christian and Farshid. And in 2024, we proved the following theorem. So there's a number field with some signature, R1, R2, and we have to have something along these lines, because if the P. Hilbert class field tower is infinite, there's no hope of constructing a field over it with P. Hilbert class field tower G, right? So you have to have some basic requirement like this. Then there exists an L over K with P. Hilbert class field tower. Or having Galois group G. And there's various cases depending on whether the p roots of unity are in the field or not, but I'm not going to really worry about that. I'm just going to write down sort of some sort of the max type thing. L over K is ramified at 2 plus log base P 3 times log base p, cardinality of G primes. And L has signature ratio R1 to R2. So for starters, you could just take K equal to Q, and we can get a totally real field, and we can control these things a little bit. Okay, so I want to talk a little bit about how one doesn't prove and then how one does prove this theorem. And we follow, by the way, what Ozaki did. I mean, there are certain places where we've simplified the proof, but I don't think we would have ever gotten there without reading his proof, and it's a beautiful theorem. I think it's perhaps
So I
not
have
as
a-
widely.
So I have
Yeah,
a question, please. Can you come back on the explanation concerning the fact that P does not divide the class number of P?
right. So what if K is our field? And what if it has an extension like this? The P Hilbert class field tower has a first step. And what if it has a second step? And what if it goes on for infinity? Well, the moment I try to build an L over K, then if I just take this composite, this will be unramified at P. And when I take all the composites, it will be. So there will always be an unramified infinite P extension of L. So you have to have this assumption, or at a minimum that the tower stable terminates at some point, the P Hilbert class field tower. Otherwise, the theorem can't be true. Does that answer your question?
All right, that's okay. So also there are conditions, the fact that K contain, the root of unit?
No, I mean, what happens is there are slightly different versions of this theorem, whether K contains the p-th roots of unity or not. I think if K does not contain the p-th roots of unity, maybe you can remove this. And if K does not contain the p-th roots of unity, maybe this becomes a 2.
Okay,
So
good.
there's some
Okay.
small, but I just wrote down sort of the theorem that applies in both situations, rather than
It
just
is-
write down 4 cases.
Thank you.
Okay. So let me tell you, first off, let me recall a beautiful theorem that's almost 100 years old now. I think in about 10 years, it turns 100. So it's the inverse Galois theorem for P groups. And the way you do this is you use a basic fact of P groups, namely that you have G will surject onto a group Gn, and we'll have an index, well, we'll have several of these such groups. And we'll
Excuse me,
further
Ravi. Excuse
Gn.
me, Ravi.
Yeah.
It's for P odd.
Yeah, probably. I want to. I mean, P odd. I think P equal 2 was done, but there were mistakes and they were corrected later. But I mean, the theorem is now true for all P. But you're right, P odd. Thank you. So when you have a P group, you can always filter it by groups where they sort of get bigger one step at a time. You can filter it by subgroups or quotients, however you want. We'll do it with quotients. And then the plan to prove the theorem, so that's the theorem, and this is the plan, use some stuff we know about P groups. P groups implies we can do this. They're solvable. And then what you do is you build a K1 where the Galois group is G1, the first quotient, which is just Z mod P. Then you build an extension where the Galois group is G2, which is a bigger quotient, and G3 and G4 and so on. And you build something at the top where you get the whole thing. Now, the reason I mentioned Schultz-Reichardt is you can't do this in our situation, even if this were a general base K, because whatever field you have here, its P Hilbert class field tower is fixed. You can't control that, right? So the idea that Ozaki has is not to do that. Still have the same filtration. As in the Schultz-Reichardt theorem. But instead, let me get my indexing correct. We're going to have a field K0. That's our starting field. Right, I call that K in the theorem. And then we're going to build a K1. And so this notation is Ozaki's notation for the top of the P Hilbert class field tower. Okay? And say this group is G1. Then we're going to have an extension K2 of K1, and this will be ramified. Now remember, this is unramified because we're solving our problem. Unramified everywhere. And then he builds this group is also G1, but he sort of slides up and then is able to get G2. And he keeps sliding up to get G3, G4, G5. And that's how you prove the theorem. There's no way you can avoid this. And what Ozaki is unable to do is control these degrees of these slides. And that's where we were able to control the degrees and the number of ramified primes. I think each degree for us is either P or P squared, and the number of ramified primes is 2 or 3. So there's fairly strong control there. This is the strategy. So plan.
So how is K0?
K0 is K, is the starting field. And its maximal unramified tower is itself because P does not divide its class number.
Oh, okay, okay, thank you. Yes.
So the plan is to induct like Schultz-Reichardt, but change the base along the way. The base case of the induction is actually not hard. You just have to get a K1 where the class number is exactly divisible by P, and that was that exercise I talked about at the beginning. That's not a problem. But it's the inductive step that takes some work. Now, as with anything with group extensions, when we go from Gn to Gn plus 1, Gn being a quotient of Gn plus 1, that quotient map, may as well write it down. This could be split or not split. You've got to treat those two cases separately. The p roots of unity could be in the field or not in the field. You have to treat those two cases separately, or at least we have to, and Ozaki as well. So there's 4 cases you have to go through. I'm certainly not going to do that here today. What I'm going to talk about is how do you do this case in, say, the non-split. So you have to do both, but I'm just going to focus on the non-split case. How do you choose a field here to make this work? And unsurprisingly, at least, well, if you've been playing this game a long time, it's actually going to come back to the Gromonier theorem a little bit. So what I want to do such that I get this Galois group if I allow ramification at this prime P1. That is a standard result in obstruction theory, and you can do that. Okay, so this is standard. It's a little bit subtle, but not too subtle. Obstruction theory. That's one thing I need. Unfortunately, I need a lot more. Well, I don't know. It's unfortunate. It made it more fun. Okay, I have to say what the 1-0 problem is for an extension like this. Remember, this is unramified everywhere. Now I'm allowing ramification at P. And what the 1-0 problem is, there has to be a unique extension. Now, P, my prime P can split into many primes here. So there could be many extensions here, above here, ramified at P. We're insisting on one. How do we do that? If you remember what I wrote down about Gromonier, it's about the number of dependence relations of the Frobenius elements in those fields, which are called governing fields, when you add in the pth roots of that V empty set thing. But the point is, it's Gromonier. And we want no extensions ramified at P down here, which is again Gromonier. There exists a unique extension C mod P extension of LP of Kn ramified at primes above P. That's mathfrak P. And there does not exist a Z mod P extension of Kn ramified at P. Both of these are Gromonier. Now, this part is not a problem. You just need a prime with a non-trivial Frobenius and an extension. This part is a huge problem. This is the hard part. Almost all the work is in making sure that that happens and that you can make that persist to happen in the inductive steps. But I don't think I'm going to get into that. I may say a few words at the very end about that. There's time. But what I want to say is why this is enough. Well, here's what we're going to do. So by the way, the primes P are going to come from Chebysherov's theorem. There are infinitely many of them. And we have this extension right here. Okay, well, let me just say P1. And it splits completely is how we choose it. And this is a technical thing, so you may be wondering, why am I writing it down? And hopefully you'll see in a second. So the first prime splits completely from here to here. The second does as well, but not from here to here. Remember, 13 doesn't split in Q root 5. That's what stopped my tower. It's the exact same thing. I mean, it's actually, there's a ton more work. This is much more involved than that little problem, but the principle is not hugely different. Just making it work is not easy. Okay, so we're going to have these two things. There's a solution to my problem, except it's ramified at P1. There's a solution to my problem, except it's ramified at P2. That Galois group is Z mod P cross Z mod P. Now, I spent most of my career in the deformation theory of Galois representations. And I had a representation, say, to Z mod P squared, GL2 of Z mod P squared, and I wanted to lift it to GL2 of Z mod P cubed, and I couldn't. So I moved to another one, and that one I could lift. And then I moved and I lifted. That was the game. You can move between these two solutions to my problem. How do you move? It turns out it's an element of H1 that allows you to move. But this is just a Hom from that big Galois group to Z mod P, and it cuts out an extension. And it's ramified at both of these. Remember how when we had Q root 65 and we went to Q root 5 and Q root 13, this was unramified because all the ramification was absorbed in this diagonal extension. Well, I'm going to base change to here, and then I'm going to sort of look at, well, I'm going to have to draw the diagram again. Running out of space. But the idea is I'm going to sort of base change this whole picture up. And I'm going to look at this field extension. But what happens is the ramification here and here, and that element of H1 collapses this a little bit. So this is no longer this group that's Gn times order P squared, cardinality of Gn times P squared. This group is the cardinality of Gn times P. And in fact, this Galois group is Gn plus 1, and it's unramified everywhere. And the reason it's unramified everywhere is we've absorbed the ramification here. Just like we absorb the ramification at 5 and 13 by the middle field. It's not quite a middle field. We're slanting up a bit. And that sort of almost solves the problem. what if this has an unramified tower? Then we lose, that we've not controlled the tower. And the answer is going to be no. And it's basically, and I'm not going to get into the details, sorry, but it's exactly for the same reason as before. 13 didn't split in Q root 5. So that's the strategy. Being able to solve that 1-0 problem is really, really a challenge. And I'll speak a few words about that now, not very much at all. And the few words I'm going to speak about it and now I've got to do that thing where I add in that V empty set, the p roots of that. I'm not going to write that down. It has a name and it's called the governing field. Now, luckily we're at the top of the tower here. So there is no class group. It's just units. So we're just adding the p roots of units in that V empty set thing. So this Galois group is isomorphic to the units of LP of Kn tensor FP dual. And we need to understand its structure as a GN module. Now, it turns out such things are always isomorphic to a free part. Direct sum, a not free part. Now, that's not very helpful because this you have no control over. It turns out that if you can make this be big, a big free part, many free constituents, then you can make this work. Big and lambda big to perpetuate with the inductive step. And that's quite hard. The inductive step. And that is what I earlier referred to as hard. There's something you have to do down here, but that part isn't so hard. But doing them both simultaneously requires a little bit of care. Anyways, maybe this is a good place to stop and I can take some questions. Thank you.
I have a question. Could you
Great.
be,
Yeah, please go ahead with the questions.
could you say what big means? I mean, in this context.
Yes. I'm just trying to remember. It's one of these things, again, I think it varies as to whether the p roots of unity are in the field, but I think we need lambda. I should probably just look it up in the paper, but it's something like this. Something along that, the number of generators of GN and the number of relations of GN.
I see.
So
So
I might have my coefficients wrong, Ralph, but it's close to that.
does that mean that n is small, unusually small?
So well, n vary. You know, if your group has order p to the billionth, n varies from 1 to a billion, and as n getting bigger, the number of generators and relations are getting bigger as you slide up that diagonal tower of fields.
Yeah, I mean capital N. Yeah.
Pardon me?
I mean capital N.
Capital N. Capital N I don't care about. That's just the torsion part. We ignore that completely. Not completely. It's not what's relevant.
Okay.
Yeah. Yeah, it's this lambda. These are called Minkowski units, and they're a relatively rare phenomenon. for them to exist. But if you need the exact opposite to prove Ozaki's theorem, you need lots of Minkowski units.
Mhm. Mhm.